This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and today I'm lucky enough to have two guests with me from the University of Georgia. Dr. Laine Bradshaw is an assistant professor in the Department of Educational Psychology. Laine, thanks for being here.
Thanks for having us, Sam.
And Dr. Andrew Izsák is a full professor in the Department of Mathematics and Science Education. Andrew, thanks for being here too.
Thank you, Sam.
We're going to be discussing their article entitled Diagnosing Teachers' Understandings of Rational Numbers, Building a Multidimensional Test Within the Diagnostic Classification Framework. And that's published in the Educational Measurement Journal, Educational Measurement Issues and Practice. But before we get to that article, I actually want to give Laine and Andrew each a chance to talk about their dissertation. So Laine, if you could maybe just briefly let us know what you did your dissertation research on.
Yeah, well, my general interest for my dissertation, I got my PhD in quantitative methods, and my general interest is in developing tests and models for test data that can efficiently provide feedback to teachers, students, and parents. And so my dissertation focused on developing a psychometric model that will use information from students' incorrect answers on multiple choice tests to be able to diagnose or to identify specific misconceptions that persisted in student reasoning. So this type of data commonly comes from concept inventories. And so I developed a model I hoped would provide a new way to provide statistically sound scores for researchers using these kinds of concept inventories.
Okay, and who advised you in that work?
Jonathan Templin, who is currently at the University of Kansas.
Okay, great. And Andrew, what was your dissertation research on?
My sort of general interest is how people reason with inscriptions. I started in grad school very interested in graphs. It was the early 90s. Multiple representations of functions was a very hot topic at the time. I ended up doing a dissertation study not on graphs but on algebra equations. I investigated how middle grade students developed novel yet sensible equations that modeled a physical device called the winch. The winch was used by Piaget for some of his studies of students' reasoning. It was picked up by Jim Greeno and used for some studies at Stanford, and then it made its way across the San Francisco Bay to UC Berkeley. And I did my dissertation work under Alan Schoenfeld. And sort of the main finding out of that was that students had criteria for evaluating equations. They might have an equation, they might understand that in some sense it worked, like they would plug in numbers and get correct answers, but they might still be uncomfortable that the equation was really a sensible model, so they had these sort of resources for critiquing equations. And just sort of say one other thing about sort of how I got from students and equations to teachers and fractions. When I started out at Georgia, I got a grant from NSF called CoStar, and it was designed to be a series of case studies, grades 6, 7, and 8, moving from fractions in grade 6 to proportional reasoning in grade 7 to linear functions in grade 8. I got really interested in the grade 6 data, and I've kind of been stuck there ever since.
Okay, great. So we're looking forward to hearing some more about that work. So you do come from different disciplinary backgrounds with educational psychology on Laine's part and then more traditional mathematics education on Andrew's side. So I was curious how you ended up getting together and working on this project together.
This project actually grew out of a previous project in which I had collaborated with some senior psychometricians at Georgia, one named Al Cohen, and the other was John Templin, Laine's advisor. We were interested in measures of teachers' multiplicative reasoning that could be used for professional development, that emphasized sense-making with things like number lines, rectangular areas. And we needed a test of reasoning as opposed to sort of recalling knowledge that's just sort of been stored in long-term memory. We had done a prior study using something called the mixture-Roche model. And we had made some progress in sort of being able to measure reasoning with that, but we knew from the research literature that multiplicative reasoning was more complex, multidimensional. We were interested in developing a test that would capture some of that complexity. Doing that required collaboration across the disciplines because we needed sort of new psychometric models and also sort of expertise in the math ed sort of cognition research around multiplicative reasoning and fractions. So I started working with John and Al, and Laine came on as a very talented doctoral student.
Mm-hmm. And you mentioned some of your co-authors, so I just want to make sure to put them on the record, Jonathan Templin and Eric Jacobson, on this article as well.
Yeah.
So you mentioned the complexity of multiplicative reasoning and fractions and all that comes with that, and I think the listeners can very much resonate with that point about the complexity. And then you talked about trying to capture that in a model. So could you say a little bit more about the goal that you set forth with this article?
Well, sort of the very broad goal was we were trying to sort of narrow the gap between approaches that were convenient for assessing large numbers of teachers, which emphasize typically recall of knowledge, not particularly sensitive to sort of moment-to-moment reasoning, and case study methods which are very good at capturing moment-to-moment reasoning, but are hard to use with samples of hundreds or thousands. So that was sort of the large challenge that we had, and we were interested in building this kind of instrument that would sort of try to sort of bridge the gap between those sort of two kinds of approaches to studying knowledge.
Mm-hmm. So speaking of the past tests or measures that exist, could you kind of characterize for us, in case we aren't familiar with what those existing tests look like?
Well, I think the main sort of, from our point of view, the main tests, kinds of tests that we had in our mind when we started out this work are tests that are very, very well known in math ed, the LMT measures of mathematical knowledge for teaching that have come out of Michigan and all the work that Heather Hill and other folks in Michigan have done. Those tests really are about stored knowledge. I mean, if you read the instructions, they ask teachers, to respond to these questions as if they were in sort of the moment of instruction in classrooms. And they also don't really emphasize reasoning with drawn models. They do have some items that involve drawn models, but they don't give you information about sort of the detailed components of reasoning that we know are out there from sort of case study work. Also, the LMT measures are deliberately designed to be used with item response theory using a unidimensional scale. So the idea is to sort of place teachers on a continuum, unidimensional continuum, from more to less proficient.
And this is true not only in mathematics education, but in educational measurement and other educational research domains. It's ubiquitous that you design tests to be unidimensional and use a unidimensional item response theory model. So in K-12 testing, large-scale end-of-course tests are typically designed with a similar psychometric model. So from a psychometric perspective, one of the goals of this project was to be one of the first efforts to build a test from the ground up that diagnosed these multiple facets of reasoning, and to, from the beginning of the test development process, understand the capabilities of diagnostic classification models and how those models were aligned with multidimensional reasoning. So we had this goal to develop a process for creating a diagnostic test like this, because there really doesn't exist in the literature or in practice examples of how to build these tests from the ground up to be used with diagnostic classification models.
So we really are, this work really is making contributions both to math ed and to psychometrics at the same time.
Mm-hmm. I'm speaking with Laine Bradshaw and Andrew Izsák from the University of Georgia about their article, Diagnosing Teachers' Understandings of Rational Numbers, which is in Educational Measurement Issues in Practice. So now that you've kind of built us up to this test and the goals that you had, could you just let us know a little bit about the characteristics of your test, and then maybe how that test works together with the psychometric model that you had in mind for the multiplicative reasoning and the fraction reasoning?
We built the test basically around 4 dimensions. In psychometric terminology, they're termed attributes, but you can think about them, sort of like, R4 if you like.
Mm-hmm.
So one of these dimensions is referent unit. So, when teachers are looking at multiplication, division situations, do they understand the units that get attached to each of the different terms, the multiplier, the multiplicand, the product? Do they understand the units that get attached to the quotient, things like that? A second dimension has to do with partitioning and iterating. There's a lot of work on children's understanding of partitioning and iterating as sort of a foundation for making sense of rational number. There's not very much about teachers' capacities. But if you're going to use number lines as sort of an instructional medium with children, you need to know something about partitioning, so that was a second dimension. A third one had to do with we call appropriateness. It's simply, when you look at a word problem or some other kind of situation, can you accurately recognize this is a multiplication situation, this is a division situation? Is it measurement division? Is it partitive division? Things like that. And the fourth dimension had to do with being able to sort of compare quantities multiplicatively. So we built a set of items that examined those four things. One of the features of these models, the DCM models, is that you can write items that use combinations of those ideas. You don't have to write items that try to isolate those. So you can write items that sort of fit more naturally into sort of the ecology of reasoning in this domain.
So that sounds really beneficial to be able to actually have items that do maybe overlap with different dimensions instead of just trying to isolate items. I also was wondering what kinds of items you had. So it sounds like you may be using some multiple representations, some different looking items than maybe have been found in the past. So I was wondering if you could say a little bit about that.
A lot of the items include number lines or area models, different kinds of sort of drawn models that you might see in sort of standards-based instructional materials. And we might imagine a multiple choice item with some diagram, and each of the choices sort of offers a different way to interpret or make sense of the diagram. And those choices are carefully constructed to try to tease out proficiency or difficulty with each of these four ideas. There is an example in the article where there's a number line. There are several number lines that are partitioned in different ways, and we ask which one of these represents, in this case actually it's a fraction subtraction problem, and the key to the item is understanding the partitioning on the number line.
And what were some of the processes that you went through to actually develop and kind of pilot these items?
At one level we did something which people often do, which is we drafted items, and then we recruited in-service teachers to take pilot versions of the items, and we were interested to see to what extent the items actually were tapping the content that we were interested in. So, we might write an item, and we thought that it would require, using, say, multiplicative comparisons, and it turned out that teachers had some other way of reasoning about the item that sort of circumvented the content that we were interested in. We were also, particularly with partitioning, because there wasn't a lot of research on teachers' partitioning, we had to sort of figure out where partitioning got hard for teachers. So, figuring out how to take a number line and divide it into four equal pieces, that's not that hard, but you can sort of ramp up the difficulty of the partitioning. So we wanted to figure out sort of where things got tricky for teachers. We went through multiple cycles of drafting items, recruiting teachers, interviewing them about how they reasoned about the STEM and the various choices that were presented to them. And I think it was at least 3 rounds of sort of trial and refinement.
And this type of work was particularly critical to the success of using a diagnostic classification model, because the model relies on an accurate input of which attributes or reasoning components are measured by each item. And so this alignment, figuring out which items measured which attributes, was a really key step in harnessing the diagnostic model to get the information that we did end up finding.
Mm-hmm. So then once you had the multidimensional tests in hand, remind me, I think you then administered it with, it was hundreds of teachers, right? Was it nearly 1,000 teachers or something like that?
Mm-hmm.
990.
So then administering that, and then when you had those teachers actually complete the tests and then looked at what you found, what were some of the results that you want to share with the listeners? Maybe we can start with results about what you saw in terms of the teachers' understanding of rational numbers and multiplicative reasoning.
So I'll just give 2 quick results. One may not be surprising for math ed researchers who work in this area, but the items that tapped referent unit for multiplication, division of fractions were difficult. And we could see that very clearly in this large national sample. The other thing that was difficult were these partitioning and iterating items. We had Partitioning iterating was probably overall the second most difficult of the attributes as measured by the items that we developed for the test. How to sort of use factors and multiples as a resource for subdividing lengths or areas into equal-sized pieces is not obvious to in-service middle grades teachers.
You also have this contribution from the article about the model itself, and I was wondering if you could say what were some of the kind of main results on that side of things.
Well, one thing the model enabled us to see is that we posited that there were these 4 distinct attributes, so that you might have a teacher who would be strong on 2 of them and weak on another 2. And from the results, we saw that we did have teachers with different patterns of reasoning. So with the 4 different attributes, you can have up to 16 different attribute profiles if you considered every possible combination of mastery and non-mastery. And what we found is that we really did have a nice spread of teachers into those different profiles. And so the model helped us see that this theory that we had about teachers' reasoning, it gave us some evidence to suggest that this theory was a useful theory, and then the model was able to reliably distinguish between these different patterns of strengths and weaknesses. For example, on this test, if you had, in the paper we have a figure that shows 3 different teachers that had the same total score on the test, which means they got the same number of items correct on the test, but because they missed different items, their estimated attribute patterns of mastery were really different. So even though the teachers had the same score, one teacher might be strong on referent unit and weak on the other 3, or they may have been weak on referent unit and partitioning and iterating and strong on the other 2. So what we saw from this is the profiles really aren't on a continuum from low achieving to high achieving like you find in item response theory, but it's really a multidimensional view of teachers' understanding and reasoning.
Yeah, I'm glad you mentioned that. In the paper, it's figure 6 for people that are actually going to be looking at the article. And I think that figure 6 really is makes a compelling point about the importance of this multidimensional test and really thinking of it in terms of multiple dimensions as opposed to just trying to line teachers up upon a single continuum. And so if listeners are interested in working in this area, or they're working with teachers, or they just have any kind of use for a multidimensional test of this sort, is there a place that they could actually find yours?
Yeah, the test is, now that it's been calibrated on this national sample, it's ready to be disseminated, and any other project that's sort of looking at teachers reasoning about fractions with an emphasis on things like number lines and area models that's interested in using it, we would love for them to contact us, and we'd be happy to talk to them and see if sharing the test with them would be a good idea.
Okay, great. And in addition to sort of contributing this test to the field, what are some of the other implications that you see for this work?
Well, I think sort of one of the large implication for the work is that it represents a significant step towards measures that capture moment-to-moment reasoning. It's a first step. If people are interested in tests that capture this kind of information, presumably other people will maybe think about other ways to do it that are better than what we've done, but it's an important step in that direction. Another implication of it is that this is could be very useful for formative assessment. Imagine administering a test and getting this kind of information about areas of strengths and weaknesses at the beginning of, say, a content course for future teachers, or at the beginning of a extended professional development experience in a school district. It sort of gives you a sense of areas to concentrate on.
Mm-hmm. Absolutely.
And sort of a third thing is that it provides ways of coordinating studies that look at large samples with detailed case studies, particularly in complicated domains like multiplicative reasoning. So you could sort of imagine an ongoing research program where you were using surveys like the one that we report in this paper, sort of understanding sort of what the distribution of reasoning looks like in large samples, and harnessing that with detailed case studies, where the case studies are being selected because sort of where they fit in this distribution.
Mm-hmm. Yeah, it gives a way to kind of interpret maybe case studies of teachers that have trouble with the referent union. And like you mentioned, it's kind of known that there are troubles with referent unit, but now we can take and really coordinate those case studies together with these sort of larger trends.
So this also sort of represents a more fine-grained approach to characterizing teachers' facility with multiplicative reasoning and understanding, sort of how representative the case studies are, because we know sort of what this distribution of profiles looks like.
Another implication for the field of mathematics education is that psychometrics as a field is undergoing a renaissance of sorts that is enabled by faster computing and software and different estimation techniques and a theoretical conceptualization that really looks at coordinating psychometric models with learning theories. And so the result of this is there's a range of new psychometric models and methods that are opening up for math education researchers to be able to use. So in some sense, this is one example of a more modern measurement technique that could be used to try to help math education researchers quantify their theories and falsify theories in a different way.
And capture the complexities that we know are embedded in a lot of these content areas. I'm speaking with Laine Bradshaw and Andrew Izsák from the University of Georgia. We're also curious in what your next steps are building forward from this work.
Well, we have a couple of next steps. One is that, this is a little bit of shameless promotion, but so be it. We are working on a JRME monograph that has been accepted, but it's still being reviewed. And the monograph is about sort of a range of psychometric models and how they can be applied to math ed research and issues that a variety of research teams around the country have encountered when trying to apply psychometrics to math ed research. So if people are interested in this sort of opening space of a wider range of psychometric models and how they might be applied, some of the opportunities that are being created there, and also some of the challenges of harnessing those opportunities, we hope at some point in the next year or so that this monograph will be out. People can learn about other things beyond just this particular model that we report in this one study. So that's one thing. Another thing is that in our own work, we are now using this measure in studying teacher education at the University of Georgia. So I'm teaching this content, a multiplicative reasoning course for pre-service teachers, and I'm administering this test at the beginning of the semester and collecting data on sort of the distribution of profiles for teachers at Georgia. Mm-hmm. So trying to investigate, how the profiles actually can be used to inform teacher education.
Another step we'd like to take in the near future is to provide a stronger validity argument for the test. So within the paper, we established that the test has nice psychometric properties and it has a high reliability in the sense that it's able to consistently assign diagnoses of mastery to the different attributes. But we'd like to gather some other evidence for validity. And one way we think we'd like to look at this is to have math education experts evaluate videotaped interviews with teachers, where teachers are completing different reasoning tasks that are similar to the types of items that were on the fractions test, but not exactly the same. And then we'd like to see if we ask an expert to determine if a examinee is a master of each attribute, could the DCM model based on the DTMR test results yield the same classification? So can we get some consistency between a math education expert decision and a diagnostic classification model decision?
Mm-hmm. We look forward to that work as well, and we thank you so much for talking about this article. Before I let you go, I do have one last question that I ask all of my guests, and this is a question from Aaron Brackenecki, my friend at Michigan State University. And I'll start again with Laine. So, Laine, if you were not in the field of education research and educational psychology, what could you see yourself doing with your life?
Well, right now, I think I want to be my brother's assistant basketball coach for his high school women's basketball team. He's coaching his first season and loving every minute, so I can't help to be a little bit jealous of the excitement. I grew up loving basketball and all things sports and coaching basketball. and teaching high school math was always something that I had a passion for and kind of saw myself doing before I kind of stumbled upon the field of psychometrics and how to integrate my background in mathematics education with test development and psychometrics.
So I'm a bit of a basketball fan myself, and now I can't believe. So we're recording this a couple days after Georgia just had an overtime victory over the University of Missouri, so this is kind of a sore spot. Thanks for bringing it up.
Go Dogs!
Andrew, same question to you. If you weren't in math education and in math education research, what would you see yourself doing?
So my totally fantastical answer is that I would have been born several decades earlier, and I'd be playing in a big band, maybe like Ellington.
Really?
I love
Any
big band.
Any particular instrument?
Well, I studied piano growing up, so any instrument, just as long as I could be in the band.
All right. Well, thank you so much for both of you taking the time to speak about your work.
Thank you very much.
Thank you.
Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.